We'll begin talking about the integers mod n. This is something that we've discussed in class as well. Let me go through it again. So this is the integers mod n, and then the units as well as the group. So we talked about the congruence mod n. M is an integer, M is positive. Means A minus B is divisible by M. And so this, like any equivalence relation, it partitions the set. This is a relation on integers z into m distinct equivalence classes. We could go 0, the equivalence class determined by 1, the equivalence class determined by n. So again, maybe just say what these brackets are. This is all integers y, such that y is congruent to x mod n. So it's the equivalence class, and we've seen that breaks it up into m different equivalence classes. So what we want to do is let's try to make this into a group. So let z of m be exactly the set of equivalence classes. So it's all equivalence classes determined by an integer r. R is between 0 and m less than or equal to m minus 1, or strictly less than m. And again, r would be an integer. So those are called the integers mod n, Zn. And is it a group? Let's try to see what we have. What's a natural way to define it? So let's, Zn, that's the integers mod n. Can we make it into the group? Make Zn into a group. And so what's the natural way? How would you add two equivalence classes of the integers mod n? Well, you take the equivalence class determined by A and add it to the equivalence class determined by B, and that gives you add AB and look at its equivalence class. And so we define that for any two of these equivalence classes. So first, is it closed? I think it should be closed because AB is just some integer. A plus B is in Z. So A plus B is some Q M plus R. Where R is strictly an integer between 0 and strictly less than M. So what would that tell us? That would tell us that the equivalence class determined by AB is equal to the equivalence class determined by R. And certainly that's an integer. We also note that when we mod out, the equivalence class determined by M is 0. Again, why is this? If you looked at AB minus R, you would have a multiple Q times M, a multiple of M, and so they're equivalent. M minus 0 is divisible by M, so that's why M is equivalent to 0. So what we have to do is show a well-defined this, so we want to look at two elements. The problem is here, suppose that A is congruent to A prime mod M, and B is congruent to B prime mod M. If we're going to define these two things are equal, then their sum should be equal. So we'd have to see, is A plus B the same as A prime plus B prime? That's the well-definedness issue. We have to check that our addition is well-defined. So what does that have? We have, since the congruent there, we have A minus A prime is equal to some K times M, and B minus B prime is equal to some J times M for integers K and J. That's because of the assumption that they're congruent. So then, if we look at A plus B minus A prime plus B prime, see, we can distribute and group these two together would give us the Km. These two together, with the minus sign distributes through, would give us the Jm. So we would have Km plus Jm. And so that's just some integer K plus J times M. So A plus A prime, or A plus B, is congruent to A prime plus B prime. Because their difference is divisible by M. In other words, we have a well-defined addition independent of the choice of representative A and B to define the product of the sum of the equivalence class of A plus the equivalence class of B to be the equivalence class determined by the sum A, B. So it's a well-defined binary operation. The other group properties follow real quickly. How about zero identity? Well, x plus 0 is just going to be x plus 0, or just x. And that's true for any coset in Zm. I said coset equivalence class, but I think we mentioned when we introduced cosets that really these are cosets if our subgroup is the cyclic subgroup generated by M. Remember, under addition, the cyclic subgroup generated by an integer of the integers under addition is just all multiples of that integer. So to say something is a multiple of M, in the group theoretical language, we're really saying that's in the cyclic subgroup generated by M. How about the identity? If we look at A plus negative A, so this is true for any equivalence class, mod n, A plus negative A. Well, we add the representatives, but that's just 0, so we've got an inverse of A. The inverse of A is, I should say the inverse of the class determined by A is the class determined by the negative or the additive inverse of A. And then associativity also follows through using the properties of the integers being associative under addition. So these three elements are elements of our group Zn. And so if I take A plus B, allow me to add that first and then add that to C. And so that's how I add A plus B. And I add that to C. So then how do I add two elements? I just add their representatives, A plus B plus C. So we'll move back to the other board in a second. This is going to be, you now use the associativity, that's A plus parentheses B plus C. Remember, we're defining the addition in terms of the representative. We've checked that it's well defined. So now this is a single integer here, so we have the associativity that we can apply to the integers. Then we just have to unwind it and see that's how we have the associativity applied to cosets. So that we can view as A plus the coset determined by B plus C. But that would just be A plus, and then in parentheses, this is exactly how we would add two cosets B and C. So Zm is associative. So we've got it well, once we have it well defined, the other properties follow pretty regularly. We have a group. Is it cyclic? Well, if we take any, for all A and Zm, the equivalence class determined by A is the same as the equivalence class determined by R. We've already proved that for some positive R between 0 and n minus 1. But this is really 1 plus 1 plus 1 R times. So in other words, we can generate any element in the integers mod n by adding the equivalence class of 1 to itself a certain amount of times. So Zm is cyclic generated by 1. Again, to help us further understand cyclic groups in the integers, the cyclic group generated by 1, we keep adding 1 to itself, we never get back to the identity. We would just get all the positive integers. Then we have to throw in 0 to have an identity. Then we have to throw in -1, the inverse of 1, and then all repeated addition of -1 to itself, and that would give us the negative integers. So that's why the integers are cyclic generated by 1 an infinite cyclic group. These are finite cyclic groups with n elements, right? Because you add 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and you keep going. When is the first time that you get 0 is when when you've added 1 to itself m times. That's the first time you can get something that's divisible by m, right? Because if we add 1 to itself less than m times, that integer is less than m, so there's no way it could be divisible. And certainly if we add 1 to itself m times, we get m, and that is divisible by m. So Zm is cyclic with m elements. How about multiplicative? Well, it does have some properties. First of all, is it even well defined? What about multiplication? So define for any two integers mod m. How would you define multiplication? Just in the natural way like that. But we have to check that it's well defined. So suppose A was really the same thing as A prime. The equivalence class determined by A was the same as determined by A prime, and likewise B. But then we need to check that the product AB and the product A prime, B prime determine the same class. So what we'll do is we'll use, I think I did this in class, and we add and subtract the same thing. So we look at AB minus A prime B, and this is A B minus A prime B plus A prime B minus AB prime. But this equals some x times m. Why is that? Well, just working here, AB, pull out this B prime, A minus B, A prime minus A minus A prime times B, plus pull out the A prime, B minus B is 0. And again, if A and A prime determine the same equivalence class, this difference is divisible by m. Same with B and B prime determine its class, this difference is divisible by m. And so the sum must be divisible by m. So we have a well-defined multiplication. And it's associative. So multiplication in Zm is well defined. And it's also associative. If I take any three elements of Zm, and again, the elements of Zm are equivalence classes. If I looked at A, B, and the product of that with C, this would be AB, product with C. Put parentheses around AB. This would be AB, C. And again, using the associativity of multiplication in the integers, we would then have that. But this is really the same thing as A times BC, which is the same thing as BC is the same thing as the equivalence class determined by B and C. We can just move this over for a second so you can see that. Again, it's just a natural way, as it is shown in the notes, the associativity of the multiplication. And again, closure is no issue because AB is again equivalent to some R with R between 0 and n minus 1. So we certainly have closure. So multiplication is closed and associative, but will it have an, is there an identity? Well, the multiplicative identity of Z is 1. It does have an identity for any equivalence class of the integers mod n. If we multiply it by 1, we would just have A times the equivalence class of A times the equivalence class of 1 is the equivalence class of A times 1, or just the equivalence class of A. But what about inverses? Well, for all x, 0 times the equivalence class determined by x this is equal to 0, which is the equivalence class determined by 0, which is not going to equal the equivalence class determined by 1. 1 minus 0 is 1. It's not going to be divisible by the mod. Because we really should take mod to be greater than or equal to 2. Integers mod 1, you can think about as just being the integers, right? A minus B are divisible by 1. Well, that basically means A equals B. That means the only thing, that would basically, mod 1 you really would be the integers, just the regular integers. So certainly in any of the other mod 2 or greater, the 1 is not equal to 0. So we have no inverse for 0. So it's certainly the integers mod n are not a group. We've seen that a lot in the multiplication. Even stuff like the real numbers are not a group under multiplication. We've got to throw out zeros. So that's a natural question. If I throw out 0 from integers mod n, do I have a group? So what if we exclude? Do we get a group? Under multiplication. Well, let's look at, this is generally not going to be the case. Let's look at Z4. 2 times 2 is going to be equal to 4, which, again, I'm saying 2 times 2, I really mean the equivalence class of 2 times the equivalence class of 2 is equal to 4. But the equivalence class of 4, which is equal to the equivalence class of 0, so if this inverse exists, then we can multiply both sides by it or cancel. Multiply 2 by 2 inverse, we get 1. And so that would just leave 2. Multiply 0 by 2, we would get 0. So we get 2 equals 0, or the equivalence class determined by 2 equals 0. That's not true in mod 4. 2 and 0 are separate equivalence classes. They're not the same. So we have a contradiction, so certainly in Z4 we don't have it. So let's see if we can generalize what's going to happen. When would you have something? Well, if m equals j times k, for j and k strictly less than m, so I guess that would make them less than or equal to m minus 1. And certainly it's not 0. M is not 0, so we can't, so j and k are also greater than or equal to 1. Then the equivalence class times j multiplied by the equivalence class times k is going to be equal to 0. And so that's going to have a problem with either j or k having an inverse, right? If j had an inverse, you can multiply by the inverse of j. You get k equals 0, but k is between 1 and m minus 1, so it's not going to be equal to 0, right? And the equivalence class determined by m is 0, but j won't reach it. And of course, the equivalence class determined by 0 is going to give us this same equivalence class, but these are at least 1. So it looks like maybe we have just some multiplication, what happens is that maybe there's some sort of common factor between m. And so that's really the key to get a group. So let's try to formalize this. So let um be all those equivalence classes in Zn such that the greatest common divisor of A and the mod is 1. No common factors. Think about it, if you did have a common factor, this is going to allow us to basically show that 0 times something, that A times something that's non-zero is would give us 0, and then that would contradict A having the identity. So that's really the key. What we want to do is from this you might think maybe what we need to pick is something that doesn't divide m. But even if it doesn't divide m, it would just have to have it can't have any common factors. So we let this UM, U stands for unit, and I claim UM is an abelian group under multiplication. We'll look at that in a second. Maybe let's look at an example of something that I thought about. If we look at in Z12, eight times 3 is 0. So the inverse of 8 cannot exist. Again, why? If it did exist, multiply it by 8, by the inverse of 8, both sides. Here we'd just be left with a 1, so we'd be left with 3. 0 times anything would give us 0, so we'd have the equivalence class determined by 3 mod 12 is equal to the equivalence class determined by 0 mod 12, and that's certainly not the case. So that's kind of an insight on why. So let's try to show why this is the case. Give a formal proof. And the U kind of stands for units. In other words, U is a collection of elements of Zn that have inverses. And so that's what we're going to need to get a group, right? We already saw that Zn is closed and it has an identity, and associative, but some elements don't have inverses, but if we look at just those that do have inverses, we'll get that. So let's see why this is the case. Let's show closure. If A and B is in UM, then AB is certainly in ZM, but is it in UM? Well, what we want to show is what is the GCD we need. What's the membership criteria to be in UM? There we need the greatest common divisor of AB and M to be 1. Remember, we're not multiplying any two cosets A and B, but we're multiplying cosets where A and B are relatively prime to M. They have GCD of 1. So we have GCD of AM equals 1 and GCD of BM equals 1. So what we certainly have is if GCD of A, B, and M was greater than 1, then that means they have a common factor, so there has to be a prime where P divides AB, and P divides M. But now by Euclid's lemma, since P is a prime, P divides A or P divides B. But if P divides M, we also have to have, since P divides M, what does that tell us? Since P divides M, then either that means since P divides A or P divides B becomes to P divides the GCD of A and M. Or even more, so P divides M and P divides A, or P divides M and P divides B. So either case we have a contradiction. This will contradict either that the GCD of A and M is 1, or the GCD of B and M is 1. So that can't happen, so the GCD of A, B, and M is equal to 1. And that's the membership criterion for AB to be one of the units of ZM in that set we call U. So we've got the identity closure. What about inverses? Well, as we often see, there exists a U and V in the integers. If the GCD of A and M is 1, that would mean 1 would be U, say AU plus MV. So that would give us then that AU minus 1 is equal to MV, which is exactly what we have for AU is equal to the class determined by 1, or the way multiplication A, the class determined by A, multiplied by the class determined by U is equal to the identity. And so the inverse of A is this identity U, and UN has inverses and thus is a group. I don't think I proved why it's abelian. It's the same argument like with the associativity. We're going to use the fact that multiplication of integers is commutative, so that's going to mean multiplication of the coset determined by integers have to be commutative. So for any two cosets in UM, this is actually true for any two cosets in ZM. AB, by definition of multiplication, is that. By familiar properties of multiplication of the integers, AB is equal to BA. And again, by definition of how we multiply cosets, that's enough to tell us that UM is a group. So let's illustrate how we can find this inverse, and we'll see how it relates to some exercises we did in the first homework assignment and on the very first lecture about the integers. maybe not the first lecture, but one of the earlier lectures on integers. Okay, so let us look at, let's find the inverse of 17 for, well, which mod is 17? It could be anything, right? I'll tell you it's for U23. So the key is that if it's in U23, then the GCD of 17 and 23 is 1. And if we could express it as a linear combination, right? Remember, that's how we've shown it as inverse, sort of the 17 times U plus 23 times V is going to equal 1, and that U will be the inverse. So let's do that. We have the GCD of 17 and 23 is going to be 1. So let's find that using the Euclidean algorithm. So what do? 17 goes into this. We have a plus 6. 6 goes into 17 twice with a remainder of 5. And 5 goes into 6 once with a remainder of 1. So there's our GCD. Why is that? Because, well, we can't get any lower than that. 5 equals 5 times 1. You stop line here. So let's try to get this back in terms of 1. So 1 is going to be equal to 6 plus negative 1 times 5. But 6 is equal to what? We see that, well, 6 is equal to 6. Okay, but 5 is equal to 17 minus 2 times 6. So 1 would equal 6 plus negative 1 times 17 plus minus times 2 would be a plus 2 times 6. So 1 would be 3 times 6 plus negative 1 times 17. Let's see that I made a mistake. No, 18 minus 17 is 1. So far, so good. And now, what's my next step? My next step, I guess, I would replace 6 by 23 and 17. So 1 would be 3 times 23 minus 1 times 17 plus negative 1 times 17. So I would have 3 times 23 minus 3 times 17 plus a negative 1 or minus 17. So that's equal to 1. I'll move it over to this board here. So 1 is going to be 3 times 23, and then that's going to be minus 4 times 17, or plus negative 4 times 17. Make sure that works. That's tough to do in my head. 96. And, no, 6 of them. It is tough to do in my head. 69. 69. And that would be negative 68, and that indeed gives us 1. So what does this mean, mod? This means 1 is going to be 3 this class times the equivalent class of 4 times 17. But again, we're in mod 23, so this is equal to 0. When I say this, I mean the equivalent class of 23 is equal to 0. So I have 1 is equal to just, that's 0, negative 4 plus 17 times 17. So the inverse of 17 is negative 4. Mod 23, what is negative 4? So think of the negative of 4. 4 plus what would take you to 0? Well, mod 23, the class determined by 23 is 0. So it would be 19. So if we wanted to represent negative 17, remember, we can choose our representatives just going from 0 to n to 22. So if we want to pick that, the equivalence class determined by -4 is the same as the equivalence class determined by 19. I did almost just from definition, I almost thought of inverse, right? 4 plus 19 is 23. So the equivalence class determined by 4 plus the equivalence class determined by 19 is the equivalence class determined by 23, or the equivalence class determined by 0. So that means the inverse of, that means the -4 has to have an equivalence class of 19. Or just from the definition, 19 minus a -4 is 23, and that is divisible by 23, so they have to represent the same class. Okay, so two questions we're interested in. What is the order of UN? How many elements are in the group? And then also, is it always cyclic? So let's start looking at that. We're looking at what is the order of UN and what is the, and is it cyclic? Harder than the integers. The integers mod n, we can answer that. How many elements are there in the integers mod n? M elements. Is it cyclic? Yes, it's cyclic generated by 1. Or the equivalence class determined by 1. So let's look at some small examples. So what is U2? So U2, what's prime to 2? Well, we throw out 0, so it's just 1, and that's it. So U2 is order 1, and it's certainly cyclic. Any one element group is cyclic, it's just the identity. Well, let's start to maybe generalize something. If P is a prime, how many elements are there in UP? P minus 1. Right? Just 1, 2, all the way up to P minus 1. Right? Because P is a prime number, so nothing smaller than P can divide it. Can't have any common factors besides 1. And 1's okay, right? The GCD of 1 in P is 1. And then everything else, the GCD with a prime, has to be 1, since all those numbers are less than P. So we get sort of the maximum amount of elements. So U3 is going to be 3 minus 1, 2 elements. And so U3 has to be cyclic. Any 2-element group is cyclic. It just has 1 and then 2, an element that is its own inverse, right? 2 times 2 is equal to 4, which is 4 is congruent to 1 mod 3. Because 4 minus 1 is 3, so that's divisible by 3. So that's cyclic. What about U4? You can't directly apply the theorem. So what's in the group? So how many elements are in U? Well, let's count. 1 is prime to 4, 2 isn't, 3 is, and that's it. But 4 obviously is not going to be equivalent to 0. So we also have 2 elements, so it's got to be cyclic. Because there's only one really 2-element group, right? You have the identity, and then you have some other element A, where A squared is B. What about U5? Well, the order of U5, the number of elements, there's 4. So there's 4 elements. Could it be cyclic? There may be, right? Remember we had that group decline. There's a group that's cyclic, and and there's a group where every element is its own inverse. So let's see if it's cyclic or not. What are the elements of U5? The coset determined by 1, 2, 3, 4. Like any prime number, U of P for P of prime, you can just start with 1, and all the cosets up to P minus 1 are included. So let's see if we can generate that cyclic group. So let's look at the cyclic subgroup generated by 2. So it certainly has 2. And it has 2 squared, which is 4. And it has 2 cubed, which is 4 times 2, which is 8. And mod 5, 8 is equivalent to 3. So I have 1, 2, 3 elements. But by Lagrange, there's got to be the number of elements in this subgroup here has to divide 4. So once we get more than 2 elements, we know we have to have the whole group. So really, after this calculation, I've gotten 1, I've gotten 2. I haven't hit the identity yet, so I've got to have more than 2 elements, but I've got to divide 4, so I've got to have all 4 elements. But we can try one more time. 2 to the 4th. Well, 2 cubed is 3, so 2 to the 4th would be 3 times 2, or 6. And again, mod 5, 6 is congruent to 1. So we've got 1, 2, 3, and 4. We've got all 4 elements. So again, U5 is cyclic. So let's move on and look at some other units mod M. How about U6? A lot of things are divisible by common factors with 6. 1 doesn't, 2 does, 3 does, 4 and 6 have a common factor of 2. 5 does not. So the order of U6, well, there's just 2 elements, that's 2. And so that's, again, got to be cyclic. All groups of order 2 are cyclic. In fact, I think we proved during Lagrange, all groups of prime order must be cyclic. And 2 is a prime. What about U7? Well, 7 is a prime, so without listing the elements, we know right away that it could be 6 elements. But we've seen some elements of order, some groups of order 6 may not be cyclic. I'm not sure if we looked at an example yet. The one example we did look at that was not cyclic was also not abelian. And all of these UMs will definitely be an abelian group. They may not be cyclic, but they will be an abelian group. So what are the elements of U7? So we have 1 and 2, basically everything between 1 and 7. And is it cyclic? Well, let's start looking at some elements that possibly generated. And again, I'll start with 2. So what's in the cyclic subgroup generated by 2? Well, there's 2, and there's 2 squared, which is 4. And there's 2 cubed, which is 2 squared times 2, or 4 times 2, which is 8. The equivalence class determined by 8. And that's the equivalence class determined by 1. And then I think that'll be it, right? We've seen the order of a group is the same, of the cyclic subgroup generated by an element is the same as the order of the element. It's the first positive integer that takes you back to the identity, right? So clearly, 2 to the 4th would just put us back to 2. 2 to the 5th, well, 2 to the 4th is 2, 2 to the 5th would have to be 4. So, might be cyclic, but 2 is not going to cut it as a generator. How about 3? What's the cyclic subgroup generated by 3? And again, looking ahead, the order of a subgroup has to divide 6. So if I can prove that there's at least 4 elements, I don't have to actually go through and find out what the 4th, 5th, and 6th elements are. Once there's more than 3 elements, there's got to be the full subgroup. So we have 3, and then we also have 3 squared, which is 9. 3 squared is 9, and mod 7, 9 is equivalent to 2. And then 3 cubed would be 3 squared times 3. Well, 3 squared is 2. 3 cubed would be 6. So look, I've got 1, 2, 3. I'm going to get the identity. So right away, this tells us that I have to get all 6 elements of U7. This shows us that U3 is bigger than 3. But by Lagrange, the order of that subgroup generated by 3, U3 bigger than 3. I mean, the cyclic subgroup generated by 3 is bigger than 3. But it's also got to divide 6. So the only way something bigger than 3 can divide 6 is if it equals 6. So we really can make an argument. We don't have to go through the computation. But let's go ahead and go through the computation. 3 to the 4th is 3 cubed times 3. 3 cubed is 6. So 3 to the 4th is 3 times 3, or 18. Which the equivalence class determined by 18 is the same as the equivalence class determined by 4. I'll stick my equals U7 over here. 3 to the 5th is 3 to the 4th times 3, which is 3 to the 4th is 4, so it would be 4 times 3, or 12. Mod 7, that is equivalent to 5. And finally, I guess I'll put it up here, 3 to the 6th is 3 times 3 to the 5th. We just saw 3 to the 5th is 5, so equivalence class determined by 5. So 3 times 5 is equivalence class would give us 15, which mod 7 is 1, because 14 is equals kind of equivalent to 0, and so 15 minus 1 is equal to 14, which is divisible by 7. So again, we have UZ is 6. So I'll take a dramatic pause now to say maybe they're all cyclic. And the reason I'm taking that pause is if we go to U8, I think that's going to be enough to show that it's not cyclic. Notice also the mod, the m, I can't just subtract 1 and say that's a number of elements. That only works when u is prime. Like u7 was 7 minus 1, 6 elements. But u8, I can't do 8 minus 1. what is U8? Well, how many elements are in there? Let's count them up. I got 1, 2 is not in there because 2 and 8 have a common factor. 3 would be in there. 5 would be in there. 6 would not. 6 may not divide 8, but it's got a common factor. 7. So there's 4 elements. But one of the 4 element group, every element was its own inverse. So that might be the case. So let's look at the cyclic subgroup generated by 3. We've got 3 and 3 squared, which is 9. But 9 is congruent to 1 mod 8. Okay, how about the cyclic subgroup generated by 5? Well, that would have 5 and 5 squared, which is 25, and mod 8, since 25 minus 25 minus 1 is 24, which is divisible by 8. So the equivalence class generated by 25 is 1. So again, I look at 5 squared, it's its own. So I think that's probably, if we looked in the group that's 4 elements that was cyclic, if you think about that Cayley table, only one element, besides the identity, there's one other element that's its own inverse, and the rest of them are not. The other 2 elements both have order 4. So I think we've shown that 7 can't work based on what we know from the Cayley table. Let's verify that. So we would have 7 and then 7 squared. Which is 49, but I think 49 is equivalent to 1 because 41 minus 49 is negative 48, and negative 48 is divisible by 8. So U8 is not cyclic. Again, the way we showed it's not cyclic is we've looked at, well, certainly the identity just generates the identity element. We looked at all the 3 non-identity elements, and we had rolled up our sleeves and examined the cyclic subgroup generated by those elements, and none of them filled up all 4 elements. None of them contained all 4 elements. So I could close with maybe a little diversion on the integers mod m, or particularly um, and get some results in number theory. So, what do we have? We have this connection is by a function known as the Euler-Phi function. So, the Euler-Phi function, and this can be generalized quite a bit, but let's define on just positive integers. N. So n is a positive integer by phi of n is equal to the number of k and g integers with k between 0 and n, and the GCD of k and n is equal to 1. So what we really have is m, or n, whatever we want to use, um, the number of elements in is exactly the value of the Euler-Phi function. Because those, after all, are going to be the units of the integer mod n for each integer between 0 and m that is relatively prime, then that's going to give us a unit. So the number of different elements of is going to be exactly the number of integers between 1 and n that are relatively prime. Well, let me, my notation, this should be n here. And so really we could actually make this a strict inequality, or less than or equal to n minus 1, right, because there's no way if k is equal to n, it's certainly not going to meet this. So that's already, see, maybe one link where these groups may come up in number theory. And let's maybe get some properties of these Euler functions. We'll state them without proof. First, for P A prime, the Euler function is just P minus 1. What about for P squared? This is just P squared. What integers do we have to throw out? Well, we just minus P, or P times P minus 1. And so we're just stating that without proof. The first one, this one, I think we understand, right? It's a prime, everything is less than it. What if it's a prime squared? Well, what you want to throw out, suppose it was 7 squared. What would you want to throw out? Well, you've got 49, but what do we kick out? We want to kick out 7 times 1, 7 times 2, 7 times 3, 7 times 4, 7 times 5, 7 times 6, and of course 7 times 7. So we want to throw out 7 of these. So that's where that comes from. Well, again, if we ignore the 49, you can think if you have 7, and you want to throw out 7 times 1, 7 times 2, 7 times 3, all the way up to 7 times 6, one less. And so for any positive integer alpha, for alpha in Z, alpha positive, phi of P to the alpha is just going to be P to the alpha minus P to the alpha minus 1, or if we pull out a common factor, P to the alpha minus 1 times P minus 1. Again, if alpha was like 3, so 7 cubed, so you have 7 cubed different numbers, which one's relatively prime? Well, 7 times 1, 7 times 2, 7 times 3, 7 times 4, 7 times 5, 7 times 6, 7 times 7. We keep going all the way up to 7 times 48, and then that would stop. And so that would give us the alpha n minus 1, right? There'd be basically 49 choices, 49 multiples of P. So that's where that comes from. So anyway, again, we won't prove these. These are just stated without proof. I'm just giving a brief heuristic argument as to why these equations seem believable. Then multiplication, is it a multiplicative function? Well, not really, but if we have two integers m and n that are relatively prime, then the number of primes that are relatively prime to the product m times m is equal to the number of primes relatively prime to n times the number of primes relatively prime to n. And you would just multiply. Again, this doesn't apply for any integers, just for the GCD, just for integers that are relatively prime. And so a particular case, if P and Q are distinct primes, right, because after all, if P and Q are the same prime, there's just P multiplying them would give us powers. But that would be in case one. But if they're distinct prime, this would equal PQ minus P minus Q plus 1, or P minus 1 times Q minus 1. You can look at it this way. It's an application of number 2, right? Certainly P and Q are distinct prime. They have they have nothing in common. So phi of P times Q would be equal to phi of P times phi of Q, which is P minus 1 times Q minus 1. Or a counted argument, you look at P times Q, okay, you have all those integers from 1 to P minus Q. What do we throw out? We want to throw out all the multiples of P. So we want to throw out P times 1, P times 2, up until Q. So we throw out Q of those. And what about the multiples of Q? Well, Q times 1, Q times 2, all the way up to Q times P. But here we've thrown out PQ twice, so that's where this plus 1 adds back in. So either way, you get the equivalent answer, I think. I haven't FOILed those out, but hopefully that works. PQ, negative Q, negative P, positive 1. So we can actually get a general formula now. Let M be in C, make M positive, so M is going to be P1 to the A1 times PQ to the A2 up to P K to the AK, where each AI is greater than or equal to 1, and PI is not equal to PJ if I is not equal to j. In other words, we factor it as distinct primes. So I want to see how we could come up with a formula for the Euler function, Euler phi function. So P of M is just phi of M is just phi of this product. But these are all, each of these are relatively prime to another, so we can multiply out. And then we end up with P1 to the A1 minus 1 times P1 minus 1. And that will continue on all the way up to PK AK minus 1, and then PK all minus 1. Again, I'm appealing to this formula and this term for each of those distinct primes. And so that's a formula, but we can actually rewrite it in an interesting way. Again, this part here is just kind of a diversion, not really a central idea of abstract algebra, but I think it's important to show how some of the group structure, particularly of these unitary groups, UM, can help have some connections to number theory. So let's simplify this a little bit. So what I do here is we can equal, so phi m equals, so I'm just continuing on with this. I'm going to maybe pull out a common factor of P1, A1, and then I have 1 over 1 minus P1. So again, it looks a little strange, but I'm just pulling this P1 out of here. So I get 1, and then I have to, but it's distributable, I have to pull it out of 1 as well. So I pull it, this factor here. But if you distribute through and multiply back, you would get this over here. And this goes on all the way, pulling out a factor of pk through here would give me pk to the ak. And then I pull it out and left with a 1. And I can write 1 is really the same thing as pk to the ak over pk to the ak. So if I pull the pk to the ak out of the numerator, then I'm left with it in the denominator. Not ak, I'm sorry, I only pulled it out to the first power. So this is going to be what? Let's collect these all together here. So I have P1 to the A1, PK to the AK, and then we have 1 minus PI, 1 minus 1 over P1 times 1 minus 1 over P2, all the way up to 1 minus 1 over PK. So this gives us a pretty neat formula for the Euler phi function. So let's see, what do we have here? Do we recognize this? This was our original prime factor. So this would be m. And then this is a product of 1 over 1 minus p, where P is prime and P divides M. So again, a little aside, just to maybe just to calculate the order. So you can also think of this as also equal to the order of UM. So there's an interesting formula way without actually listing the elements to try to calculate UM. Yeah, it's probably a lot easier to just list the elements. I just wanted to go through and develop this theorem, or this formula. And so let's try something like, what is the order of U36? Or how many numbers between 1 are prime, between 1 and 36 are prime to 36? So this example, we look at phi of 36, so it's going to be 36 over what? What are the primes dividing 36? So 2 is a prime, that goes in, 3 goes in, the next prime is 5, that doesn't work, next prime is 7, that doesn't work, next prime is 11, that doesn't work, and I think actually once we hit 6, there can't be any primes bigger than 6 that are factors of 36. So it would be 36 times 1 minus 1 over 2 times 1 over 1 minus 3. So that's 36 times 1/2 times 2/3. So this is 12. This is 6, so it's just 6 times 2, or 12. So anyway, using that formula, we can find the number of primes between 1 and 36. The number of integers relatively prime to 36 between 1 and 36. There's 12 of them without actually going through and counting them. Okay, so let's move on, and we'll conclude now with using the structure, some of the structures of the group, with 3 famous results from number theory. So let's get a general result about a group. We can call this a theorem or a fact. Let G be a finite group. We claim for all G and G, if I take G and I raise it to n, that gives me back the identity. Or put another way, for all G and G, G raised to the order of G gives you back the identity. So why is that true? Well, we know for all G and G, G raised to little g is just the identity. That's because the order of G is in a finite group is the smallest power that takes you to the identity. So in particular, G raised to G takes you to the identity. But what does that tell us? Well, for all G and G, really the way we define the order of an element is the order of its cyclic subgroup. So by Lagrange's theorem, the order of this cyclic subgroup divides the order of G. So the order of little g divides n. That's the order of big G. So n equals little g times k for some integer. That's since this order divides n. And so if we look at G to the n is G to the order of G times K. By properties of exponents, that's G to the order of G raised to the K, but that's just the identity. And so that completes the proof. So this fact seems pretty basic. It's going to be important to get some of these number theory results that in any group, if we take any element and we raise it to the power of we raise it to the order of the group, we get the identity. Now that may not give us, that may not be the first time that we get the identity. It's not saying that. It's not saying the order of little g is the same as the order of this group big G. No, it's just saying that the order of big G is one such power that takes you to the identity. It need not be the smallest power, positive power. In other words, it need not be the order of the element itself. And so sometimes you might see, this is a little bit of pound, but you can define the exponent of a group G is the smallest positive integer t with G to the t being the identity for every element in the group. And sometimes we write, again, not a very common notation, EXPG for the exponent of G. So I call the Klein 4 group, that cyclic group where every element was its own inverse, that was an example of a the group, the exponent of that group would be equal to 2. Think about what it means to be cyclic. If you can find the exponent of G is equal to the order of G, that's really what it means to be. That's one way you can show something is cyclic. Okay, so let's prove some results in number theory now. We have three famous theorems that I like to prove using the structure of the UM, of the multiplicative groups of the units of the integers mod n. So, recall, thus, for all A in UP, where P is prime, if we raise this, we would get back the P minus 1, we would get 1. And again, that's just because we saw UP, so that P is prime, UP, the order of UP is P minus 1. So any element in that group of order P minus 1, if we raise it to the P minus 1 power, we get back the identity. So let's, first of the three theorems is little Fermat's theorem. So this is for any integer A and any prime P, P, we have A to the P is congruent to A mod P. So let's look at the proof. We'll split it in two cases. Case 1, if GCD of A and P is equal to 1, then if A is relatively prime to P, that allows us to think of A as being an element in UP. So A to the P minus 1 has to be 1. So if we multiply both sides by A to the P minus 1 times A, I say A, I should be saying the equivalence class. And the equivalence class of this, well, that just means A to the P minus 1 times A. Again, I'm putting in a ton of details, probably too many. And finally, that gives us that. And that's what the brackets mean. Two elements generate the same equivalence class means they're equivalent mod M. Or A to the P is congruent to A mod P. So that's case 1. Case 2. GCD of A and P is not equal to 1. Well, since P is a prime, the only GCD with P and something else would have to be P itself. In other words, P divides A, so P divides A is equivalent to 0 mod P. And certainly A to the P, if we multiply 0 by itself P times, A to the P would still be 0 mod P. Thus, since A is congruent to 0 mod P and A to the P is also congruent to 0 mod P, A is congruent to A to the P mod P. And that completes the proof of Little-Fermat's theorem. So again, see how this result in number theory, famous result proved by Fermat in the 1600s, can be proved pretty easily from the structure of groups, really, from some basic facts of groups. Mainly the Lagrange theorem, to me, is really at the root of this, because that's what gave us the fact that allowed us to show that if we raise any element to the multiply any element by itself, the number of times that you multiply it is the same as the number of elements in the group, you're guaranteed to get the identity. Then we have a version of this for Euler's theorem. We'll prove that in a second. So Euler's theorem again, let m be a positive integer with GCD, A, and M equal to 1 for A and Z. Then if I look at A raised to the phi of M, that's the Euler phi function, that is also congruent to 1 mod M. So let's look at the proof. Since the GCD of A and M is equal to 1, we can think of the equivalence class determined by A of being in UM. But we just saw how many elements are UM? They're the number of elements between 1 and M that are relatively prime to M. That's exactly the Euler phi function. So since the order of UM is this Euler phi function, A to the Euler phi function has to be congruent to 1, or not congruent, let's just say it's equal to it. Right? An element raised to the order of the group takes you back to the identity. Well, the way we multiply cosets is multiplying the representative. So this coset is the same as that coset, or that equivalence class. I say cosets because mod M is really an example of being in the coset. Divisibility by M is equivalent to the coset you get by the cyclic group generated by multiples of the cyclic subgroup generated by M. And so we have that congruence. Open up our P. Mod M. So that proves Euler's theorem. Okay, and the last theorem I want to prove is Wilson's theorem. So Wilson's theorem is, actually we'll just prove one direction. It's actually if and only if statement. But we'll only prove one direction. So we'll only state, really this may not be Wilson's theorem, this may be a partial bit of Wilson's theorem. This is our third famous theorem of number theory. Let P be a prime. Then P minus 1 factorial is congruent to negative 1 mod P. And it actually goes the other way. If you have an integer P where P minus 1 factorial is congruent to 1 mod P, then that integer has to be a prime. We will not prove that. We will only prove this direction. And once again, we're going to use the structure of the units mod M, or in this case mod P. So proof. In UP, we have, well, if we multiply P factorial, it's 1 times 2 times 3 times P minus 2 times P minus 1, and that equals P minus 1 factorial. And so this product contains all P minus 1 elements of the units of the integers mod P. So we've got them all lined up. All right, let's sort of try to think about how this would work. What you can do is you can pair up something with its identity. It's commutative, right? So if something is in this product and it's got an identity that's something different, we can pair them up, bring them together, that product would be 1, so in effect you could remove it from the product. So really what we're able to do, if we look at that product with P minus 1 elements, it appears to be P minus 1 elements, but we can take out everything that is not its own inverse. Right? Take this P minus 2, its inverse is somewhere in this list, unless it is P minus 2, but if it's not, we can match it up with its inverse and the product would be 1 and remove it. Again, in the notes I tried to word this. If X is not its inverse, so if the class determined is not its inverse, will be separate members of the product. When I say the product, what product do I mean? I mean 1 times 2 times P all the way up to P minus 1. And we can commute to arrange X times X minus 1, which is equal to 1. So really we can remove X and X inverse from the product. And so ultimately what we want to do is this product is p minus 1 factorial. We'd like to show that it is in fact equal to negative 1. So really what we have to do is what's left. The product will therefore only have elements x that is its own inverse. So the things that aren't their own inverses, they'll match up, multiply in pairs, you get 1, you can remove them. What's left standing after the dust settles? Just everything that is its own inverse. But what is its own inverse? Well, what do we need? We need, if an element is its own inverse, that means A times A is the identity, 1. So that would give us A squared equals 1. So we have that. So let's maybe work with this mod notation. That's same thing as saying A squared is congruent to 1 mod P. So what does that tell us? Let's bring it over to the other side. A squared minus 1 has to be congruent to 0 mod P. So A minus 1 times A plus 1 has to be congruent to 0 mod P. But remember, UP is a group. Each of these elements are elements of UP, so they have inverses. So since A minus 1 and A plus 1 have inverses, we can conclude what? Well, if we look at this product, if we multiply by the inverse of this, we get that A plus 1 has to be congruent to 0 mod P. Or the only other way that can happen is if this could be 0, or if not, if this is not 0, then this would have to be 0. Okay, let me pause there for a moment. If A plus 1 wasn't 0, we could take its inverse, multiply by it, and get A minus 1 would have to be congruent to 0 mod P. But if A minus 1 is not equal to 0 mod, not congruent to 0 mod P, we can multiply by its inverse and get A plus 1 is equal to 0 mod P. So one of those two cases has to happen if the product is equal to 0. Right? If neither one was equal to 0, that would lead to a contradiction. So what do we have? We have A has to be congruent to minus 1 mod P, or A is congruent to 1 mod P. That's the only way we can have an element A that's its own inverse. And let me just offshoot this. If this is true, then that means A has to be congruent to P minus 1 mod P. Right? Because P minus 1 would be P minus 1 plus 1, or just P, would be congruent to 0. So the only elements of UP that are their own inverses are 1 and P minus 1. Thus, if you look at P minus 1 factorial, you have that huge product, but everything else will meet up with its inverse and cancel it out, and we'll just be left with 1 times P minus 1, or P minus 1 factorial. 1 we can get out, and P minus 1, we've already seen that's the same as the equivalence class determined by 1. So what does that tell us? If the equivalence class by these two elements are the same, they must be congruent to each other mod P. Okay, so again, this is a little bit tangential from the main focus we've been looking at in abstract algebra, but I just wanted to bring in some number theory connections and prove kind of these theorems historically are important. They have an interesting history. They're pretty fundamental results. And they all come, the proofs all come fairly easy using the group structure. So we'll stop here and we'll begin talking more about some cosets in our next lecture. Well, I say more about, we've already talked about cosets. We'll be seeing how we can impose the group structure on cosets. And that's the same way, really, we've done that already with the integers mod n is a group of cosets.